A very warm welcome to one and all to this next topic of the series, which is Deterministic Finite Automata or DFA. In our previous videos, I have also mentioned quite many times that FSM is the basic model of a finite automata. I will show you in detail in the later part of this particular video what are the various differences between an FSM and a finite automata. Let's first of all see what exactly is a finite automata and what are its classifications. Finite automata is a machine which, when receives some kind of an input, does some operations on it and produces an output. Fixed number of inputs, fixed number of outputs. That is a finite automata. Hence, it's called as finite. It can be basically divided into two types: deterministic finite automata (DFA) and non-deterministic finite automata. That is, determinism is a word. Deterministic. Why do we call it deterministic? Because in case of DFA, there is a fixed number of inputs, fixed number of outputs, and fixed number of states. Okay, so that is why we call it as a deterministic finite automata. We'll see in the later part the various classifications of it. Similarly, NFA. NFA is non-deterministic in nature. That is, the inputs, outputs, and the states of a non-deterministic automata may vary. For example, a DFA can never make a transition on a blank input, or for example, whether there is an input or not, the NFA may make any transition from state Q0 to state Q1, but in the case of a DFA, it will always expect some kind of an input, then only it will make a transition to any other state. That is the difference between NFA and DFA, the basic difference. Clear? So now let's see the classifications of DFA and NFA. DFA comes in two flavors, with output and without output. That is, we saw in few examples of FSM, for example, binary adder. Binary adder was a problem which was showing outputs for each state. So that is a type of an finite automata where we expect some output for each state. Whereas all other problems, wherever we haven't mentioned any output for each state, those come under the second classification of DFA, that is without outputs. So we have already seen the problems based on without outputs. Now we will be seeing two classifications of DFA with output. Those are Moore machines and Mealy machines. The problems on these will be dealt in much detail in the upcoming videos, where we will be focusing only on Moore machines and Mealy machines. Similarly, NFA has two classifications, with epsilon and without epsilon, where epsilon stands for null. So NFAs can make transitions either on some input or without any input as well. So these are the basic classifications of NFA. So that is how we classify a finite automata into DFA and NFA, further into with outputs, without outputs, and NFAs with epsilon and without epsilon. So this is the major classification of FA. So now let's focus our attention to DFA. This is how we can relate an FSM with a DFA or NFA. Let's see the left hand side. We are having an FSM. We told you that FSM consists of only three tuples, that is I, O, and S. I stands for inputs, O stands for output, and S stands for states. Whereas on the right hand side we can see that DFA consists of 5 or 6 tuples. 5 in the case of DFA without output or NFA without output, and 6 tuples in the case of with outputs, because there will be one more tuple added, that is this lambda, which corresponds to output symbol. So you can clearly see that the FSM consists of IOS, whereas DFA consists of summation, that is this sigma symbol, Q, and this lambda corresponding to I, O, and S. So inputs are nothing but this, outputs are nothing but this particular symbol, and S, that is finite set of states, corresponds to this Q symbol. Rest other symbols are also meaningful, which are corresponding to initial state Q0, final state F, and transition function. Now what is this transition function? If you remember the implementation table which we used to draw, inputs on one side and the states on the other side, this is nothing but your transition table. or transition function. Clear? So this is how we relate an FSM with a DFA. So let's see a problem based on DFA, because it will make the things much clearer how exactly a DFA works, and the differences or comparison between an FSM and a DFA will be much evident. So let's see how it works. The question is, design a DFA. Now the terms have changed. Previously we used to write design a FSM. Now design a DFA to accept the strings ending with 011. The logic remains exactly same. Let's see where it differs. Step number 1 is same theory. In this case we need to write the theory about a DFA and not about an FSM. Okay, so step number 2 is logic. Here what exactly we do is we write the same table that is we used to write for an FSM, states versus inputs, the same kind of a table over here. We already know how to solve such a problem ending with 011, right? It's basically ending with logic. Okay, so ending with 0, obviously q0, q1. Similarly, ending with 1, it becomes 10. 10 means it will land up in q0 only. So we know how to construct such a table. After constructing the table, you can see I have done something over here. What is this thing? What exactly do you mean by this? This is nothing but, you can see we have merged certain states. These states are QS and Q1. Now what is merging? According to the rules, merging can happen between two states which are either final states or non-final states. Either final or non-final. This is one of the conditions. The second condition is that the transitions of both the states have to be same. For example, in this case we have merged QS and Q1. Why? Because we can see that QS and Q1 are both non-final states, whereas the final state being Q3. So QS and Q1 are both non-final states, so this condition is satisfied. The second condition is they have to have same transitions for the same input. For example, QS on 0 gives Q0, Q1 on 0 again gives Q0. Similarly, QS on 1 gives Q1 and Q1 on 1 also gives Q1. So in such a case, when both the conditions are satisfied, then only we can merge two states or minimum two states. Here we have merged QS and Q1 together and we have named that as a state Q1. So now initially QS was my start state. Now my start state will get converted to Q1 because we have merged QS and Q1 together. Clear? So now let's see what is step number 3. Step number 3 is implementation. Carefully pay attention over here. In the case of FSM, we used to write 3 tuples. In this case, we are having 5 tuples because it is obviously a finite automata without output. So we won't be having 6 tuples. We will be having only 5 tuples as mentioned previously. Clear? So the 5 tuples are Q, sigma, transition function, initial state and final state. So the number of states, obviously we have to write the states after merging. So the number of states are Q0, Q1, Q2 and Q4. It has reduced to 4. Initial state Q0 is nothing but Q1 now because we have merged QS and Q1 and combined it to a state called as Q1. Clear? Final state obviously is Q3, the inputs being 0 and 1. The fifth tuple or over here transition function has to be explained properly. So what we are doing is, this is your transition function, the table which we have or the table which we get after minimizing or after merging any of the inputs or any of the states in the above logic. We get something like this. This is your transition function. Clear? So based upon that transition function, we know how to draw a transition diagram. It's very simple. Pay attention over here. Now the initial state is not QS or Q0, it is Q1 because we are referring it from this particular tuple, which is Q0 is nothing but Q1. So initial state is nothing but Q1. So we have to start our assumptions or start our transition from Q1. It's already marked over here. You can see the marking over here which signifies that Q1 is the initial state. So this is how a transition diagram is drawn in case of a DFA, and the final step also remains same, which is simulation or example. We know how to solve an example, so I'm not focusing much on that. I just wanted to show you how exactly a DFA is similar to a FSM and what are the various steps in which it differs from an FSM. So this is all about the first lecture on on deterministic finite automata. In the next lectures we will be focusing on finite state machines with outputs, or DFA with outputs and DFA without outputs. That is Moore machine and Mealy machines. So that's it for this lecture. Stay tuned for the upcoming lectures. Thank you for attending.